How do black holes pull in light? Okay, so there is like a magic sentence that gets said when somebody is talking about black holes. It is so dense and its gravity so large not even light can escape it. But if photons have no mass, then how can they be pulled in? If we know that mg, then if mass is 0, then the acceleration of the light towards the black hole should equal 0 no matter what. Black holes, and anything else with mass, doesn't pull in objects or light, they pull in space. It's a lot like being in a current of water, you need to accelerate just to stay in place. A black hole is like a waterfall, the speed of water space is so great that you can't overcome it. The black hole's warping of space-time acts as a sort of lens, bending the light's path so that it doesn't come out of the black hole. The black hole's immense gravity is the source of the warped space-time, but that gravity isn't pulling in photons, but more like trapping them. This is just my basic understanding of how to describe it. Gravity is gravity, but if you look at it like the light is being lensed, it makes sense that even light with no mass can be affected in this way. The event horizon of a black hole is the surface that describes when the gravitational pull of the singularity, the center of the black hole, would require an escape velocity that equals the speed of light. Perhaps obvious, but light travels at the speed of light, so the event horizon is the surface at which light can no longer escape. The equation for escape velocity doesn't care about the mass of the object escaping, only the mass of the object being escaped. The best way I have heard it explained is that within the event horizon, space is curved so much that all directions lead in. Any direction you travel will eventually lead you to the center of mass. Some will take longer, you can orbit for a while, but eventually, all roads lead to the singularity. OMG. That's not even dimensionally correct in Newtonian physics. A g in Newtonian physics, assuming you mean g as in the gravitational acceleration. Really, in Newtonian gravity, a gmr2, where g is the gravitational constant and m is the mass of the source of gravity. If you notice, a does not depend on m, the mass of the object being influenced by the gravity, including when that mass m0 x 200b. Newtonian gravity predicts light bending in a gravitational field, BTW. The simple answer here is that space itself is falling into the black hole at the speed of light past the event horizon. There is no chance for anything in space to escape, including light. A good analogy would be water to space and a waterfall to a black hole. Water itself is being pulled by the waterfall. A fish, as in light, that's swimming in the water has no chance to escape past a certain point, the event horizon. Don't think of gravity as something that pulls in massive objects. Think of gravity as something that pulls in space. So when we travel in a straight line, a geodesic, through space, gravity isn't pulling us off course toward the source of the gravity. Instead, gravity is pulling space in such a way that our geodesic curves toward the massive object. It doesn't matter how much mass you have. Every geodesic is affected the same way, including ones followed by light. Black holes are only special in that once you cross the event horizon, every geodesic ends at the center. You got a lot of great answers already. I would only like to point out the glaring misconception. If we know that mg, that's certainly not true. Both a and g are accelerations, with the same unit. If the above were true, m would have no unit. Since we know m has a unit of kg, the above can't be true. Gravity is often modeled as a deformation in space. Classically, it's a bowling ball on a stretchy rubber sheet. Light always follows the surface of the sheet, so its path is bent by sources of gravity. The Google keywords are gravitational lensing. Black holes produce a deep enough pit that the path the light takes doesn't just bend and fling out at a different angle, it bends inwards and spirals into the pit, never to be seen again. They do not pull in light. Black holes, mass, bend space-time, but we'll call it space so much that instead of wrapping space around itself like a circle, it's even tighter than that. Once light enters this zone of tight, there is no path back out, so the light can only move forward in, never escaping. The point of no return is called the event horizon. The event is when you've crossed that line of no return. Since light never comes out of a black hole, they cannot be seen, hence appear black, when it's really just lack of any light at all. Put a 50 kilograms weight in the middle of a trampoline, get a marble and roll it around the outer edge of the trampoline. The weight in the middle will bend the trampoline, as such, the marble will fall into the center. Trampoline space-time. Weight black hole. Marble photon. Doesn't matter if it has mass or not, a bend in the fabric of space-time will affect all things. When we say that photons have no mass, we mean their mass is so unbelievably tiny that you count it as zero for any calculations that you might have to do. Same goes for electrons. But that doesn't mean their mass is actually zero. It's just a very close approximation of zero. Their mass is so low that they behave as if they have zero mass, that is until they encounter a gravitational force that is as insanely high as their mass is low. Like a black hole, for instance. I mean, the other answers are correct. But you could also estimate this the Newtonian way and be like, let photons have a mass mp, work through the maths and you will see that mass get cancelled out, then you have a general expression for how a particle is accelerated by a large body assuming no force is acting on the large body. It's a decent approximation. A black hole is effectively a bend in space-time, and it's not so much you're sucked in. The classic bowling ball on a trampoline, but imagine being on that slant. Like a car on a hill, it's easier to go down rather than up. The directions you can travel in that car once past the event horizon all result in you tumbling down eventually, leading to the singularity. When light enters the orbit of a black hole, it just means that every straight line through space-time eventually goes to the singularity. The best way to understand it is that black holes don't really change an object's trajectory. The object continues on a straight line, but the straight line is actually curved in an extreme way by the mass of the black hole. The same happens to the moon, for instance. One could say it goes in a straight line, but that straight line is turned into a circle by the Earth's mass. Can you conceive why light lenses around massive objects like neutron stars and such? Because the space around that object is warped by gravity? The gravity within a specified radius of a black hole is bent so much the lens is perfectly spherical. All the possible paths through that space curve into the center of the black hole. The photons are not exactly being pulled in the sense of something on a string, they are moving in a straight line through space-time. However, beyond a certain point, the event horizon, the gravity curves space-time so much that all paths the photon can take eventually fall towards the singularity. How fast do you have to throw a baseball to get it to leave the surface of Earth and never come back down? It's like 27,000 miles per hour. How hard do you have to throw a baseball to get it to leave the surface of a black hole and never come back? If that number is greater than the speed of light, that means light can't escape either. That's a simplistic answer, and I'm sure you can find more detailed ones that involve curvature of space-time, etc. In general relativity, light travels in a straight line through space-time, but gravity can bend space-time. A black hole bends space-time to the absolute extreme that it is essentially curved back on itself, and so all directions are bent towards the black hole when you are past the event horizon.